Welcome to Pre-Calculus. Today we will investigate exponential growth scenarios focusing on the growth of money deposited in accounts with compounded or continuously compounded interest. Let's take a look at three versions of one deposit scenario. So we'll head over to our notes screen. So here's the situation. Georgiana goes to the bank to open a savings account. The banker offers her an account with an interest rate of 5.6% compounded quarterly. Georgiana would like to deposit $6,000 initially, and she does not plan to make any further deposits. How much will be in her bank account after 5 years? Let's give ourselves an equation that we can use to calculate this value in the account after 5 years. Now, there's some key words in the question that tell us what sort of equation to choose. And really, it's right here after the interest. We are looking at something that's compounded, in this case, quarterly. Now, our formula for compound interest, let's write that over here on the side. Formula for compound interest is a version of what we've been seeing with our exponential growth functions. So it's A at t, so this is some future amount of money that depends on the amount of time that has passed, so we're calling it A of t, equals the principal, which is the amount that's initially deposited, times the base, which is 1 plus the rate over n. N is the number of times the interest is compounded each year. And then we're raising that to the power of that same number n times t, which again is about how much time has passed. So what we need to identify for this particular situation where Georgiana's depositing money are these variables. We need to identify what's the principal. And again, the principal is the initial deposit. We also need to find the R, which is the interest rate. We also need to find this value of n, and that's showing up in two spots. So n is showing up in the base and also in the exponent, is the number of times interest is compounded in 1 year. Number of times interest is compounded in 1 year. And then we finally want to find what's the t. And for us, t is in years. Always has to do with time. Specifically, our unit here is years. And if we can plug those values in, then we can evaluate this function for the future amount after 5 years. So the principal, if we look back in the words, is the amount that's initially deposited. That's going to be this $6,000. The R is the rate at which the interest is going to grow. So that's 5.6%. One thing we need to note for us is that that needs to be as a decimal, not as a percentage. So we would always move that decimal point 2 to the left. So I'm going to call this 0.056. That's an equivalent decimal for 5.6%. Now our n value is usually the word that follows the word compounded. So for us, that's this quarterly. And we just have to ask ourselves, how many times in a year would I compound the interest if I was doing it by quarters? That is going to be, if you think about how many quarters are in 1 unit, that implies that the number is 4. We'll give some other examples of how intervals of compounding the interest in a moment, but let's just calculate this one first. So our t value is the amount of time that we're interested in passing, and that's 5 years. So we've gathered our 4 pieces of data. We just need to substitute them here in our compound interest formula. So what we're calculating is really A at 5. What's the value in the account after 5 years? So that's going to be P, which is 6,000, times the base 1 plus. So that 1 plus is always there. The rate 0.056 over the n value. We found that was quarterly, so that's 4. To the power of 4, that n value shows up twice, times also in the exponent 5 years. Now that's the setup. What we need is a approximate value. So let's head over to our calculator to put the burden of this calculation on Desmos. And we'll just type that in. We're only going to use this feature on the left just now as we wrote it. So 6,000 parentheses 1 plus 0.056 over 4. Let me fix my error here. Not question mark, but plus. Divided by 4. And you select to the right in the cursor to get out of that denominator. To the power. So I'll choose this a to the power of b to get to the power of 4 times 5. And that looks like after 5 years, Georgiana can expect to have $7,923 and about 38 cents. Let's head back to our note screen to finalize that answer. $7,923.38. Well, let's take a look at a second view where all we're changing is the n value. Now, we said that we should look at some other possible words that would give different numerical values for n. So these are the words that we can keep our eyes open for. So annual would indicate an n of 1. Biannual would indicate n of 2. We saw quarterly, that's 4 times in the year. You can try to predict what other intervals we might expect. Monthly for sure. That's 12. We could also see bi-monthly. And what we would indicate with that is that would be every 2 months. So there's 6 of those intervals in a year. Weekly. And definitely there are 52 weeks in a year. We could also do daily. And that n value would be 365. So depending on the word that comes after the word compounded, you have a different number for the n value. So here's our second situation. Georgiana gets a second offer from another bank for 5.6% interest compounded daily. So nothing's changed except for this n value. Our n value is now 365. How much will be in the second account after 5 years if Georgiana were to deposit the same $6,000? So just like we had set for our first example there, we're going to pull our 4 variables and we want to define those numerically. So 6,000 is still the principal. The rate is still 5.6%, which as a decimal is 0.056. The n value is daily, so 365. There's 365 days in a year, and we're still interested in 5 years passing. Let's calculate then A at 5 for this scenario. So again, not much has changed. And really what we need to think is, will she have more in the account if she compounds the interest more frequently? The same or less? What do you think? So 0.056 over 365. So that's where that new value appears. It also appears in the power, 365 times 5. So again, I want to put this calculation burden on Desmos. So I'm going to head over to that graphing calculator. And I'm going to highlight this. So I'm going to select it with my mouse, and I'm going to hit Control-C to copy it. And I'm going to paste it. And all I'm going to change is this end value. So 365 in that denominator and 365 in the power. And that gives us this value, $7,938.61. So if we compare that to what Georgiana would have got if she compounded it quarterly, that is definitely over 25 more dollars. No, 15 more dollars. So it's not a huge difference, but generally speaking, as we compound interest more frequently, the growth of the money is greater. Let's head over to our note screen to finalize that answer. So A at 5, when I'm compounding it in this way, is going to be $7,938.61. Keep in mind, this is representing a situation where Georgiana only makes one initial deposit. So it's a simplified version to see what happens if I just deposit an amount at a certain interest and let it grow. Well, that is two scenarios that deal with the same values but different compounding intervals. Let's take that to the extreme. So for our third scenario, what we've got written here is Georgiana receives a third final offer from a bank for 5.6% interest, compounded continuously. I'm going to underline that word because that's a different scenario. How much will this be in this third? How much will be in this third account after 5 years if Georgiana were to deposit $6,000? So what I got to note is that still the principal is $6,000. The rate is also still 5.6%, which as a decimal is 0.056. The end value is not mentioned. That word that followed compounded was the word continuously. And what we'll see is how that changes our formula in a moment. Our t value is still 5. So the only thing that's changed is that how frequently am I going to compound the interest? Well, the truth is, if I see that I've got continuously compounded interest, so it'll always be in the words in the scenario, I have a different formula. It is also A at t, so the future amount in the account equals the principal, but instead of that base, 1 plus r over n, I have our natural number e. So really this is an application of that exponential base e. Remember that had a value of about 2.71. To finalize this, it's e to the power of r rate times time. So in a way, it's a simpler formula. Let's use it here. So I want to calculate A at 5. So again, my principal is 6,000, but now my base is simply E to the power of 0.056 times 5 years. So just like we had done, and really in this case, I really need to go to the calculator because that base E is so irrational. It's hard for me to calculate with E. So let's type it in as we had written it, 6,000 times base E to the power of 0.056 times 5. Now we need to think about what compound continuously means. First, we'll grab our answer. So it's still $7,938, but it's higher than if I had compounded it every day. It's 78 cents instead of 61 cents. So definitely in a small example like this, $6,000 is a relatively small amount to save. If you were a wheeler and a dealer moving millions, this difference in the interval of time that I calculate the interest within the year makes a big change. Let's go back and finalize that. So we'll head over to the note screen. So that value is about $7,938, but now higher at 78 cents. So what is the difference between compounding at a certain interval, for instance, quarterly, monthly, weekly, daily, and compounding continuously? What continuous compounding interest implies is that we are compounding the interest at every moment. That means that in one moment, I'm going to get some interest growth on a certain principal, and then I'm going to add that interest back into the principal, and the next moment calculate the new growth based on that added amount. So if you think the end value for compounding continuous interest is infinite, it's every moment of the year we're compounding the interest. Okay. Just to highlight the difference between these three functions, I want to go over to Desmos and just take a look at what those functions might look like on a graph. So I'm going to bump over here. Now I've scaled this graph differently. So notice the y-axis is from 5,500 to 8,000. And I'm looking at x values from 0 years up to 6 years. So it's a different view of the graph. And what I'm going to do is I'm going to type in those three functions. So we'll call the first one a of t. And that'll be the function where I take that $6,000 and calculate the interest compounded every quarter. So that's the end value of 4. But I'm going to leave it with just a variable. So now this is kind of a slice of the exponential function. So you can see a slight curve in that graph, but it almost looks linear the way that we've zoomed in on it. Let's also put, we'll call it b of t, is when I compound the same principal, but change my, so 0.056, change my interval of compounding to every day, so 365 to the power of 365t. Now, we can't see a huge change immediately, but notice over here on the right side of the graph, that green line starts to increase over that blue line. We'll zoom in a moment just to highlight that change. But let's get our third function, the compounded continuously. So c of t equals 6,000 base e to the power of 0.056 time. So there's our three functions, and we can see that that purple function is very close to the one that's compounded daily. But let's zoom in so we can see the changes real clearly. So I'm just going to kind of narrow in again on this graph, and let's look from 4.5 years to 5.5 years, and we'll really narrow in on the amount as well. So we'll go from 7,500 to, in fact, let's make that even closer. So 7,900 to 7,980. And what we're interested in seeing here is that this blue function, the one that was compounded quarterly, is always going to be less than the green one. Now I'm going to turn off the compounded continuously. So what we're seeing is that the continuous and the daily interest are very close. If I turn it back on, it looks like it's almost right on there. I'm curious to see if I can separate those two graphs. Maybe if I go from 4.9 to 5. So I'm going to adjust my domain there. And then I can probably zoom in from 7900 to 7920. Let's see if that separates the graphs. And yeah, that zoom in can highlight the change now. So now we definitely see there's a difference between the purple and the green. The purple's above the green, and this blue line, which represents quarterly interest, is definitely below. So if I type in a line x equals 4.95, definitely we can see at 4.95 years, I'd have $7,901.38 if I was doing it quarterly. If I was doing it daily, it'd be $7,916.41. If I was doing it continuously, it'd be $7,916.58. Okay, so definitely something to think about as you get ready to deposit and invest money in different kinds of accounts. Thank you for joining for this investigation of exponential growth scenarios. See you soon.